Hello, everybody. Thanks to the organizers for letting me come speak with you today. As was just said, my name is Nathan. I'm talking about the generalized Terwilliger algebra of the hypercube today. So as a quick overview, for any distance regular graph, there's a surjective homomorphism, which we denote natural, from its generalized Terwilliger algebra to its Terwilliger algebra. Now we know that this map is not an isomorphism in general, but it is in some cases. So in this talk, we will show that natural is an isomorphism, specifically when the graph is the hypercube. So the first little bit of this talk is just going to be laying down the groundwork and some basic theory. It'll probably seem familiar to those of us in this workshop because many of the things are things that we've already talked about, but it'll be nice to do it in a way where you see how I'm talking about these things and what the notation is that I'm using in this presentation. To start off, let gamma denote a finite, undirected, connected graph without loops or multiple edges with vertex set X and edge set E. We say vertices X and Y are adjacent whenever they form an edge. Let partial denote the path length distance function for gamma, and we let D be the maximum possible distance between any vertices of X. We call D the diameter of gamma. Let matx of C denote the set of matrices with rows and columns indexed by our vertex set and entries in C. Let C to the X denote the column vector space with coordinates indexed by X and entries in C. As a consequence, we get that matx acts on C acts on C to the X by left multiplication. Vertex X, let gamma of X denote the set of vertices that are adjacent to X. We say that gamma is regular with valency K if the number of neighbors of X equals K for all vertices. Okay, so some quick examples. We can see that cycles are regular graphs. The valency would be 2. You can see the 4 cycle and the 5 cycle pictured there. Complete graph on n vertices would also be regular. In that case, the valency would be the number of vertices minus 1. You can see K3 and K4. Platonic solids would also be regular graphs. The cube and the octahedron are pictured there. In those cases, the valencies would be 3. And so in addition to being regular, all those previous examples share a property called distance regularity. So again, some of this should be familiar, but we say that gamma is distance regular whenever for any integers h, I, and j between 0 and d and any pair of vertices x and y such that the distance between x and y is h, the number of vertices z such that the distance between x and z equals I and the distance between y and z equals j is a constant depending only on h, I, and j and not on the vertices that we chose. So this constant, we denote it by phij, and it's called an intersection number. Now, again, there's multiple ways to formulate this definition. This is how we're formulating it here. And this definition is a little bit of an eyesore, so it's easier to see with an illustration. So let gamma be the cube, and let's say we want to calculate the intersection number P312. So you would pick 2 vertices, call them x and y. You can see they're opposite corners in the diagram, and pick them such that the distance is 3. So P312 is going to be the number of vertices which are distance 1 from x and distance 2 from y. And so you can see that there's 3 vertices that satisfy those conditions. They're highlighted in yellow. Therefore, P312 equals 3. And again, what makes a graph distance regular is that it didn't matter which vertices I chose for x and y. Any pair of vertices that were distance 3 apart would yield this same number of yellow vertices. Now for h, I, and j between 0 and d, note that phij equals phji, basically saying that it's symmetric with respect to your choice for x and y. From now on, we assume gamma is distance regular with diameter at least 1. Gamma is regular with valency k equal to p011. Find the distance matrices. For I going from 0 to d, we define AI to be the matrix in matx of C with xy entry equal to 1 if the distance between the vertices x and y is equal to I and 0 otherwise. And so we call AI the ith distance matrix of gamma. So as an example, suppose gamma is the 4 cycle. and we're going to come back to this example several times throughout the talk because it's kind of an easy example. So you can see that the diameter d is equal to 2 because that's the maximum distance we can achieve between any two vertices. The distance matrices are given below, and so I'm ordering the vertices in the rows and columns by the numbers given on the graph. We can see that A0 is just going to be the identity matrix. A1 is going to, again, have a 1 on any XY column where X and Y are distance 1 apart. Then A2 looks like that. So the distance matrix AI is symmetric with real entries for I going from 0 to D. A0 is equal to the identity matrix. We saw that in the example. Turns out that's always the case. And A1 we'll pay special attention to A1. So we'll abbreviate it by A, and this is just called the adjacency matrix. Now, an interesting consequence of gamma being distance regular is that if I take any two distance matrices, AI and AJ, and I take their product, the result is the sum for H going from 0 to D of PHIJ times AH. Again, those intersection numbers are cropping up. And so this should sort of drop a hint here. We take these intersection numbers and they're going to behave a little bit like structure constants, to use an algebraic term. And so these distance matrices thus form a commutative, form a basis for a commutative subalgebra of Mat-X, which we denote by M. Okay, M is called the Bose-Mesner algebra of gamma. And A, again, our A1, our adjacency matrix, generates this algebra. So let's go back to our example. You can look here and sort of verify this process. You can look at the different products. So for instance, you could look at A1 times A1, and the fact that it's 2A0 plus 2A2 would tell you that P011 equals 2, P111 equals 0, and P211 equals. So define Ki to equal P0II for all relevant values of I. Ki is called the ith valency of gamma. And so for any vertex, Ki is going to be the number of vertices which are distance I from X. And so K0 is always going to be 1, and K1 is going to equal K, the valency that we identified earlier. Again, if we go back to the for cycle, fix X to be one of the vertex in that upper left corner. We highlight vertices at distance 0 from X in yellow, distance 1 in blue, and distance 2 in red. And so if you just count those, you can see that K0 is equal to 1, K1 equals 2, and K2 it's going to have D plus 1 distinct eigenvalues. And so we denote them in descending order, theta naught, theta 1, etc., through theta D. Now for I going from 0 to D, let EI in Mat-X of C be the matrix that acts as the identity on the theta I eigenspace and 0 on all other eigenspaces of A. So by construction, we get that A is equal to the sum I going from 0 to D of theta I times EI. These matrices satisfy the following two important equations. First, that EI EJ equals Kronecker delta IJ times EI. This is basically saying that these EIs are mutually orthogonal idempotents. Okay, and then secondly, very important, is that the identity is equal to the sum of EI going from 0 to D. So we call these matrices the primitive idempotents of M or of gamma, the graph. And the primitive idempotents form a basis for. Now, again, back to our example of the for cycle. If you were to calculate these things out, you'd find that our first eigenvalue is 2, then theta 1 equals 0, and theta 2 equals -2. And we give the primitive idempotents. You can look at these, E0, E1, and E2, and if you were to play around with them, what you'd find is that indeed any one of them squared will just give you back the same thing. If I take any two distinct choices and take their product, I'll get 0. And if I were to add them all up together, indeed, you would get the identity. So if you sort of were to stare at them for a minute, you'd see. Now, for any matrices B and C in Mat-X, let B circle C denote their entry-wise product. So it turns out that our Bose-Mesner algebra M is closed under this operation. So we're going to let PHIJ star denote the scale for I, H, I, and J going from 0 to D, denote the scalars such that EI circle EJ is equal to the cardinality of x to the -1 times the sum for h going from 0 to D of PH, IJ star, EH. Now again, why should these things exist? Well, again, it's because the primitive idempotents give a basis, right? And then M is closed under this operation. So we know these scalars exist. We were just calling them PHIJ star. Okay? So PHIJ star is real and non-negative. And then we call the set of these numbers the Krein parameters. Now, in our example of the 4-cycle, we have the following. So you can look at, say, E1 circle E1. That 1/4 is the cardinality of x to the -1 out front. And then inside, you could see, for instance, that P011 star is equal to 2. Now, for I going from 0 to D, define Ki star to equal P0 II star. We call Ki star the ith dual valency of gamma. Ki star is going to be the dimension of the theta I eigenspace of the adjacency matrix A. So in our example that we've been talking about, you would get 1, 2, and 1 for these dimensions. So now fix any vertex of x, and we're sort of just, for the next section of the conversation, we're just fixing a vertex. It doesn't really matter which one it is, but we're just doing one for technical purposes. For I going from 0 to D, define EI star, could also be denoted EI star of x, to be the diagonal matrix in MatX with YY entry equal to 1 if the distance between y and our fixed vertex is I and 0 otherwise, right? So in our example, the matrices E0 star, E1 star, and E2 star are given as follows. If you look at where there's our fixed vertex x, you can see that it is the only vertex that's distance 1 away from itself. So we would just have 1 in the corner and 0 everywhere else. For E1 star, you can see that there are vertices 2 and 3 are distance 1 from x. So we would have 1s on those diagonals. And then lastly, there's E2 star obtained by a similar. So by construction, these follow very similar rules to our EIs. They're mutually orthogonal idempotents, and they sum to the identity. So we call these the dual primitive idempotents of gamma with respect to our fixed vertex x. And so these form a basis for a commutative subalgebra called M star or M star x. And we call M star the dual Bose-Mesner algebra of gamma with respect to x. Now let's define some diagonal matrices AI star, right? Because we have, right, to refresh, we have AIs, we have EIs, we have EI stars. We should also have AI stars, right, to finish this duality. So here's how we're going to do it. We're going to define AI star to be the diagonal matrix with YY entry equal to the number of vertices times the XY entry of EI, right? So we call these the dual distance matrices of gamma with respect to x. Just how A0 was equal to the identity, A0 star is also equal to the identity. And we abbreviate A star to mean A1 star. And we'll, again, just how A1 sort of had properties that we wanted to pay attention to, so does A1 star. We call this the dual adjacency matrix of gamma with respect to x. So in our example, you can see how we compute AI star for I from 0 to D. You can see, again, we're just taking the XY column of EI and we're essentially diagonalizing that column. So you can see the same, there's E1 and E12 versus A1 star and A2 star. Now by construction, AI star times AJ star is going to be the sum for H going from 0 to D of PH star IJ times AH star, right? Now these form a basis for our dual Bose-Mesner algebra, and just how A generated M, A star generates M star. Now we're going to define scalars theta I star such that A star is equal to the sum I going from 0 to D of theta I star times EI star. These are the distinct eigenvalues of A star, and we call these the dual eigenvalues of gamma, the graph. So in the case of our example of the 4-cycle, we would have theta naught star equals 2, theta 1 star equaling 0, and theta 2 star equal to -2. So recall that, again, we have two different bases for M. So we'd like to consider transition matrices between those. And we're just going to define scalars Pij and Qij for I and j between 0 and d that essentially do this for us. So we get Ai equal to the sum of j going from 0 to d of Pi of j, Ej, and then Ei, basically we stick a scalar out front for aesthetic purposes, and then j equals 0 to d of Qi of j times Aj. So again, these just would be essentially the entries of the transition matrices. And so in the case of the 4 cycle, you can see this is what those scalars would look like. Now we're essentially just going to do the same thing with respect to the dual. So we'll look at Pi star and Qi star, and then we use them in virtually the same way. And then you can, again, look at what the similar equations would be, and you can pick out those scalars. Right, so we'll mention a few facts about these transition matrices. It turns out that P1 of I, by definition, would just be equal to the theta I we defined earlier. Theta I star would also be equal to P1 star of I. And it turns out from the way that we define these objects that Pi of j is actually equal to Qi star of j, and then Qi of j is equal to Pi star of j. So in fact, all you need is Pij and the dual, or Qij and its dual, or some combination of that. You don't need all 4 of them necessarily, because you get these pairs that are the same. We're going to define an object here that's going to be pretty important to what we're talking about. So the Terwilliger algebra, denoted T, is going to be the subalgebra of MatX generated by M and M star, right? So in our example with gamma, where again we just fix any vertex to be x, turns out that T, our Terwilliger algebra, is 10-dimensional, and it is algebra isomorphic to M3, just your set of 3x3 matrices, direct sum C. This proposition by Terwilliger shows how M and M star are related. So it turns out that for h, I, and j between 0 to d, EH star times AI times EJ star equals 0 if and only if the intersection number PHIJ equals 0. And EH AI star EJ equals 0 if and only if PH star IJ equals 0. So you get this duality here. Now the above equations are called the triple product relations. Now pardon me while I take a moment to sort of philosophize, but this is interesting because we have these objects that are very combinatorial, right? And how they're defined, right? We have a graph and we're looking at distances between vertices and stuff, and then we're looking at these matrices, and then out pops these very strong algebraic relations, right? In many graphs, you can get lots of these intersection numbers to be 0. So you actually can get quite a few of these triple product relations. So they're very powerful. It's sort of natural to ask the question, if you're looking at it from an algebraic standpoint, how much of the structure of this Terwilliger algebra is actually captured by these algebraic relations, right? I mean, how much of it comes from the combinatorics, how much it comes from this really strong algebra. So that's what this next object sort of aims to discover. And so let cal T denote the C algebra with 1, defined by generators and relations in the following way. This was defined by Agee. Okay, the generators are x naught through xd and x naught star through xd star. And then the relations are as follows. We have x naught equals x naught star equals 1. So this should remind you of a naught equals a naught star equals the identity. Then we have xi xj equals the sum for h equals 0 to d of ph ij xh. So again, that should remind you of the product of ai times aj. And then we have the same with respect to the dual, again invoking the ai, the interaction of the dual distance matrices. And then lastly, we have eh star xi ej star equals 0 if the intersection number phij equals 0, and the same with respect to the dual. And then in those relations, we make a point of saying that these EIs that we bring up, because those weren't listed in the generators, right? These are just going to be these linear combinations of the XJs and the XJ stars that, again, should look familiar these are these look like representing the EIs with respect as a linear combination of the AIs, right? We're using those same constants, okay? So we call T the generalized Terwilliger algebra associated with gamma. No, these are very long titles. So to be quick, I will often, to distinguish between T and cal T, I will call one the concrete T algebra and the other one the generalized T algebra. So that's oftentimes how I'll distinguish between them. Okay. So in our example we were doing, this generalized T algebra is 10-dimensional, and it's algebra isomorphic to M3C direct sum C. Again, that looks familiar. That was actually what the T algebra was isomorphic to. So we're going to talk more about the interplay between these two. So this is very important. Again, this is by Agi. There is a C algebra homomorphism natural from the generalized T algebra to the concrete T algebra, which sends xi to ai, xi star to ai star, ei to ei, and ei star to ei star. Again, this is not surprising given the relations that we defined. And because those things generate, T natural is surjective. Okay, so suppose gamma is the 4-cycle. Our example that we've been doing. These are both 10-dimensional C algebras, the concrete and the generalized T algebra. And so natural, because it's a surjective homomorphism, must actually be an algebra isomorphism. Here's the question. We know that this surjective homomorphism exists. In the example we've been following, we saw that it was an isomorphism. So is it an isomorphism in general? In other words, do the structure constants and those triple product relations, do they capture the entire essence of the Terwilliger algebra? Now, the answer is, unfortunately, it doesn't seem to be the case in general. And in fact, while T is obviously finite dimensional, the generalized T algebra can be infinite dimensional. However, we will shortly define a family of graphs called the hypercubes, for which this algebra is actually an isomorphism, and this sort of works out how we would want it to. And so, but before we get there, let's discuss a few other general properties about the generalized T algebra. So we have the following 6 statements. 1, the xi's form a basis for commutative subalgebra of T, which we denote by C. The elements ei, I going from 0 to D, form a basis for that same subalgebra. And the restriction of natural to C induces an isomorphism from C to the Bose-Mesner algebra M. And then 4, 5, and 6 are the same with respect to the dual. So in other words, we have an isomorphic copy of the Bose-Mesner algebra and the dual Bose-Mesner algebra living inside our generalized T algebra. And now we have the following results, again, just showing you that this generalized T algebra really does behave in a similar way to our concrete T algebra. We get that the EIs and the EI stars both sum to 1. We get that they're mutually orthogonal idempotents. And we have the x1 and x1 star are this same linear combination, and x1 is this theta I, the sum I0 to D of theta I EI, and then x1 star is the same with respect to the dual. Let's now recall the hypercube. For D at least 0, define QD to be the graph with vertex set X consisting of D tuples with the coordinates either being -1 or 1. We say 2 vertices are adjacent whenever they differ in exactly 1 coordinate. And so this graph QD is called the D cube or hypercube. Again, this is a Hamming graph. So here are some examples. So we have Q2 would just be the square that we've been using, the 4-cycle, and then Q3 would be the 3-dimensional cube. And so we can see that this name hypercube is actually a good name. It looks like what you'd want it to look like. So QD has 2 to the D vertices. It's distance regular. And for the rest of our talk, we're going to focus on this family of graphs, QD. We have some formulas below for the intersection numbers and the Krein parameters. It turns out they are equal, and they are the PHIJ and the PHIJ stars. They're equal to 0 if h plus I plus j is odd and equal to this sum of, or sorry, this product of binomial coefficients if the sum of the indices is even. And then, you know, we take care, the above lines, to interpret and choose m to be 0 if m is less than 0 or if m is greater than n. Now, for I going from 0 to d, we get this nice 3-term recurrence among the distance matrices. So we get a times ai is equal to I plus 1, ai plus 1 plus d minus I plus 1, ai minus 1, and the same with respect to the dual. So now let z just be an indeterminate, right? And then let us formally define CZ to be the C algebra of polynomials over Z, in Z over C rather. And so now based on the previous 3-term recurrence, we define the following polynomials in CZ. So we define fi for I going from 0 to d to be the polynomials in CZ such that f naught equals 1, f1 equals z, and then zfi equals I plus 1, fi plus 1, plus d minus I plus 1, fi minus 1 for I between 1, at least 1 and less than d, right? And so again, the point is that from the way we define them and from the 3-term recurrence earlier, we have ai equals fi of a and ai star equals fi of a star. So we have this now just convenient methodology to write the ai and the ai stars as polynomials of a and a star. So we list the eigenvalues and dual eigenvalues. They happen to be equal. Turns out theta I is equal to d minus 2i. Now, if we define the following polynomial, phi d to be the product I going from 0 to d of z minus d minus 2i, based on the previous slide, it follows that that's going to be the minimal polynomial of a and also the minimal polynomial of a star. Again, because that d minus 2i inside the product is equal to theta I and theta I star. So to get the transition matrices for QD, you can see the formula below. Again, much of this about the hypercube is well known. This has been, many of these constants and numbers have been known for a while. You can find them in various places. But yeah, we get the qij equal to qi star of j is equal to 1 over 2 to the d times d choose d times that hypergeometric series. Okay? So now this is something that I've sort of defined just to make some of these things convenient. Let the set PD consist of the 3 tuples h, I, and j of integers that satisfy the following conditions. So 1, we want h, I, and j to be between 0 and d. 2, we want h, I, and j to satisfy the triangle inequality. 3, we want h plus I plus j to be to be at most 2d. And then 4, we want h plus I plus j to be even. The consequence of defining this set this way is that phij not equaling 0, phij star not equaling 0, and the triple hij being a member of PD, these are all equivalent. And so again, if you were to go back and look at the formulas for phij and phij star, and you were to look and see, okay, when exactly are these things 0, or when are these things not 0, you'd find that it's exactly when it's a member of the set PD. So this is just a formality. It's a convenient way to talk about when these numbers are 0. So as some convenient notation, let TD denote the Terwilliger algebra of QD. And now there exists a C algebra isomorphism from TD to the sum of full matrix algebras MD plus 1 minus 2K, K between 0 and D minus 2. This is proven by Go. And I want to make a point because it actually does matter to this talk to sort of visualize what this sum looks like, right? It's MD plus 1 of C direct sum MD minus 1 of C direct sum MD minus 3, so on. It actually is important to sort of understand what that sum looks like. So let's talk about the generalized T algebra of the hypercube. We'll let cal TD denote the generalized Terwilliger algebra associated with QD. Our aim is to show that this natural map is an isomorphism. So because natural is, we already know it's a surjective algebra homomorphism, it's sufficient to show that the generalized and the concrete T algebra have the same dimension. So we'll actually do a little bit better than this, though. We'll directly show that the generalized T algebra is isomorphic to that same direct sum of full matrix algebras that Junie Go showed about TD. So our goal, in other words, is to prove that the generalized T algebra is isomorphic to that same sum of full matrix algebras, namely MD plus 1 minus 2K of C, K going from 0 to D minus 2. So first, let's make some more observations about the generalized T algebra. If you think about natural and remember that it induces isomorphisms between to this, these isomorphic copies of the Bose-Mesner algebra and the dual Bose-Mesner algebra inside the generalized T algebra, you get that the xi's and the xi stars satisfy kind of a similar three-term recurrence that the distance matrices. And so then similarly, we can write xi as a polynomial in x1 and xi star as that same polynomial in x1 star. And a consequence of that is that TD is generated by x1 and x1 star. So this gives us one way to sort of view the generalized T algebra as being generated by x1 and x1 star. And we get that phi d, that same minimal polynomial of a and a star, is in fact the minimal polynomial of both x1 and x1 star. So now I told you that, viewing it as generated by x1 and x star is one view, but because these things are linear combinations of EI and EI star respectively, we can see that the EIs and the EI stars also generate TD. And so that gives us sort of a different view, a different presentation for the generalized T algebra. And so that presentation would look something like this. Okay, we said the generators are E naught through ED, E naught star through ED star, and we'd have the following relations. One, we would have that the EIs sum to 1. 2, the EI stars would sum to 1, and then we would get these following triple products. H star, Xi, EJ star equals 0, again, if our Hij is not a member of PD, and then the same with respect to the dual. Where in the above lines, because again, now the Xi's are the ones that are not defined as generators, we would specify them where X1 and X1 star are those linear combinations of the EIs, and then Xi and the Xi star would be the given polynomials of X1 and X1 star. So now this is sort of critical to understanding why this natural map is going to be an isomorphism. There's an important element in the generalized T algebra denoted by U naught. U naught is equal to 2 to the d times the sum for I going from 0 to d of the ith valency, the -1, times EI star, E naught, EI star. So we call this element the primary central idempotent of the generalized T algebra. And so the following things hold about U naught. Agi showed this. We get that we get that the way we define U naught is symmetric with respect to the dual, so that's nice. 2, we get that U naught is indeed a non-zero central idempotent of TD, which is good since we're calling it the primary central idempotent. It better be a central idempotent. And then we get that these are very important right here. We get that TD U naught is a two-sided ideal. TD 1 minus U naught is a two-sided ideal. And then we can write TD as the direct sum of these ideals. And then lastly, that TD U naught is isomorphic as a C algebra to MD plus 1C. Now I want to highlight those points 5 and 6, because remember what our goal is, right? Our goal is to show that that TD is isomorphic to this direct sum of full matrix algebras. And 5, look at what 5 does. It writes TD as a direct sum of smaller algebras. And then 6 tells us that one of those summands is actually isomorphic to one of the summands that we're looking for, and specifically the largest summand, MD plus 1. right? And so if you take 5 and 6 and you literally combine them, you just get this corollary. TD is isomorphic to MD plus 1 of C direct sum TD 1 minus U naught. And so this is immediately a step in the direction of what we want to show. So this is sort of what, this concept is sort of what gave the springboard for the proof, which I loosely sketch below. So you start with looking at the base cases. You look at T naught and T1. Then you prove that this ideal generated by 1 minus U naught is actually equal to TD minus 2, right? So in other words, we're finding T, two, you could think of it as dimensions, 2 dimensions lower, right? We can find that generalized Terwilliger algebra. And then if we use 2 with the summand that we wrote earlier, again, we can write that TD is isomorphic to MD plus 1C direct sum TD minus 2. Then you can just use induction, and that gives us exactly the formula at the top of the slide. So this is sort of the idea that allows us to really nail down the proof. And so the base cases are quite simple. T naught is just by definition isomorphic to C, and that lemma there below tells you that the primary central idempotent in T naught is equal to 1. So this ideal T1 1 minus U naught is just equal to 0. And then the corollary makes it pretty apparent that T1 is isomorphic to M2C. So that takes care of the base cases. Now, next, because we want to show that this ideal of TD is isomorphic to TD minus 2. And so you do that with a map. Now, what's cool is that the map is actually quite clean. When I was first working on this, I didn't necessarily expect the map to be so nice, but it works out really well. So on the one set of generators, the EIs, what it does is it just sends EI to EI minus 1 and EI star to EI 1 minus star. Where again, the index, we just, for instance, E negative 1 would be 0, for instance, if the indices go out of bounds, basically. And then the other set of generators, the X1 and the X1 stars, it just sends them to the corresponding generators in TD minus 2. So again, a very, very nice map, actually, in practice. And so in that lemma at the bottom of the page, you can look at what the kernel is equal to. And then it turns out that the kernel, if you play around with it some more, is precisely equal to that ideal that is the summand that we want to quotient by to get our isomorphisms. Everything works out perfectly. And so again, because the kernel is the TD U naught, and then because TD is this direct sum, we at the bottom of the page, we get the isomorphism we were looking for. TD times 1 minus U naught viewed as a quotient algebra is isomorphic to TD minus 2. So we get this direct sum that we wanted. TD is isomorphic to MD plus 1 C direct sum TD minus 2. And so then inductively, you can get that it's exactly the full sum of matrix algebras that we wanted. Moreover, the generalized T algebra and the concrete T algebra are isomorphic. And so again, because we now have a surjective algebra homomorphism between 2 finite dimensional C algebras, we can immediately say that natural is an isomorphism. And so we've shown that for the hypercube, this highly combinatorial object, the Terwilliger algebra, is actually captured entirely by these algebraic relations, right? The structure constants and the triple product relations capture the entire essence of the object, which is pretty cool. And so the natural question, right, is because this hypercubes, I mean, they come up a lot, but it's a pretty narrow family of graphs, right? So we want to know, are there other families of distance regular graphs in which the same phenomenon occurs, where the concrete T algebra and the generalized T algebra are isomorphic, maybe broader families. And so our next conjecture that we're working toward now is we suppose that gamma is a distance regular polynomial bipartite graph, right? Let T and T denote the generalized and generalized Terwilliger algebras respectively. Then we think that natural from T to T is an algebra isomorphism. So that's sort of where we want to go next. We think that we can broaden this family of hypercubes to distance regular Q polynomial bipartite graphs, because the hypercubes are a subset of that set of graphs. All right, so in summary, just to wrap it all up, we reviewed some of the definitions and preliminary results about these algebras. We recalled the hypercube. We examined its T algebra. We next looked at the generalized T algebra of the hypercube, and we looked at an alternate presentation. We constructed an inductive argument to show that the two algebras are isomorphic. And then, we ended with an open question and a conjecture for possible further research. So thank you for your attention. I cannot hear anyone in the audience right now. Oh, there we go. I can hear you a little bit now.
So anybody have a question or comment? Yeah.
One question. So, do you know any examples whose generalized Terwilliger algebra is not infinitely dimensional?
Sorry, let me make sure I heard that right, 'cause it's a little fuzzy. I ask if I know any examples of generalized Terwilliger algebras that are not.
That are infinitely dimensional.
I'm so sorry, my audio is a little bit fuzzy. Could someone make it close?
Infinite dimensional.
Oh, infinite dimension, yeah. So I don't have any on hand, but Eric Agi, the author of the original paper, from what I understand, he has some, and so I need to talk to him at some point and look at those. But as far as I understand, not any nice ones. And it's a little bit interesting because the generalized T algebra, we talked about it kind of in this context of the distance regular graphs, but you can do them for any character algebras, and so I think definitely you get some infinite dimensional ones from there as well, because those are a little bit less structured.
I think for a general strongly regular graph where there are no extra vanishing intersection numbers or Krein parameters. So for example, as long as the A, it's not bipartite, it's not dual bipartite, so no extra vanishing intersection numbers, then the generalized T algebra should be infinite dimensional.
Because it's naturally, if you just look at the presentation, right, it's sort of surprising that it would even be finite dimensional, right? But say you need lots of triple product relations to sort of pare it down, right? And so, yeah, what Paul said, if you have something that really kind of minimizes the number of triple product relations, it should be, so anything without sort of any kind of extra niceness attached, it should probably be infinite dimensional.
So the Terwilliger algebra, the concrete one, is semi-simple. Is the generalized one also simple?
What about that, Nathan?
I'm so sorry. Could someone closer to the front repeat the question?
Here, no, you hear better. Yeah, I was just wondering if also the generalized Terwilliger algebra was semi-simple.
Oh, I believe it is. Yes.
I don't think so, because because if it's going to be infinite, so in general, infinite dimensional.
Oh yeah, no. Yeah, I take that back. I mean, certainly the concrete T algebra is semi-simple.
Yeah.
But yeah, no, actually, I take back what I said. Yeah, I don't think in general it is.
Yeah, in fact, Eric Agi, who defined this generalized T algebra in the first place, he has a paper about the diameter 2. He says explicitly that it's not semi-simple, and he looks at indecomposable modules for this generalized T algebra. Yeah, so let me just stick in a question or a comment. So we could wonder, comparing the generalized T algebra with the regular T algebra, is there some relation, something beyond the triple product relations that we're familiar with? Is there some relation that we're missing that always holds for any let's just say any Q polynomial distance regular graph that we could add, this extra relation that we could add to the list of defining relations for the generalized T algebra to make it closer to or actually isomorphic to the concrete T algebra.
I just make sure that the generalized Terwilliger algebra does not depend on the base vertex.
Yeah, that's a great question because we sort of slide through that throughout the presentation, right? But because when we talk about the concrete T algebra, right, we do it all in terms of a base vertex. We've actually it's probably too far back for me to find it. But if you were to look at the way that it's actually defined, all you really need are the intersection numbers and the Krein parameters. And those are not defined with respect to a base vertex. Yeah, so oddly enough, the generalized T algebra actually does not really depend on a choice of a base vertex.
Yes, so if your conjecture, if the Terwilliger algebra is isomorphic to the generalized Terwilliger algebra, then it means the automatic Terwilliger algebra does not depend on the base vertex any longer. So
And it would only depend on the parameters, right? So when you do, for example, it's more of a generalized algebras. But
So,
not as more of concrete ones.
yeah, that's right. So, and anytime you can find two concrete, two actual the same intersection numbers, different T module structure, that certainly those are going to those T's are not going to be isomorphic in generalized T.
Very much.
Okay, thanks.